You know, we are constantly swimming in this sea of invisible energy. It's what's warming up your food, it's carrying your favorite songs through the air, and it even lets doctors see right inside the human body. So today, we're going to explore this hidden world and uncover the one single concept that connects it all, the electromagnetic spectrum. But first, let's start with a little mystery from a place you probably see every single day, your kitchen. Seriously, think about it. You can stand there and watch your food cook, right? So light is obviously getting through that door. But the microwaves themselves, which are powerful enough to boil water, are totally trapped inside. How is that possible? I mean, they're both just forms of electromagnetic radiation. They're made of the exact same stuff, particles called photons. So why in the world does a simple metal grid treat them so differently? Well, the answer lies in one key difference between them. And that answer is found in one really elegant, all-encompassing idea that organizes every single type of light, both the stuff we can see and the stuff we can't. This right here is the key to everything, the electromagnetic spectrum. Now, it's not a collection of a bunch of different things. It is a single, continuous range. The only, and I mean only difference between a radio wave and a gamma ray is how much energy it has. And that energy level determines everything else, like its wavelength and its frequency. So, check out this slide. It shows this really simple inverse relationship that governs the whole thing. Low energy waves, like radio waves, have really long wavelengths and low frequencies. But high energy waves, like X-rays, have super short wavelengths and high frequencies. Think of it like a seesaw. When one goes up, the other goes down. And this single difference in wavelength, well, that's what solves our microwave puzzle and dictates how every type of wave interacts with the world. Okay, so let's take a quick tour of the neighborhood, shall we? We'll start at the low-energy, long-wavelength end and travel all the way up to the high-energy, short-wavelength powerhouses. We'll start down here with the gentle giants of the spectrum. These waves have wavelengths that can be as long as buildings or even mountains. They're not super energetic, but they are absolutely fantastic communicators. And this brings us right back to our puzzle. So, a microwave oven uses waves that cause polar molecules, like water, to flip back and forth billions of times a second. That rapid jostling creates friction, which is heat. Now here's the solution. Those microwaves have a wavelength of about 12.5 centimeters. The holes in that metal grid on the door, they're only a few millimeters wide. So to that big, long microwave, that grid is basically a solid wall. It just bounces right off. But for visible light, with its teeny tiny wavelength, those holes are like wide open windows. It sails right on through. This here shows exactly how we use these long waves for communication. We take a plain old carrier wave, and we just slightly tweak it. We either change its height, its amplitude, for AM radio, or we squish and stretch its frequency for FM radio. That tiny little change is what carries all the information for music, news, and phone calls across huge distances. All right, let's move on up to the middle of the spectrum. We're heading to a sliver that's so incredibly narrow, yet it's so important that it defines our entire perception of the world. This is it. Everything you have ever seen with your own two eyes exists in this one tiny little band of energy. From red, with the longest visible wavelength, all the way down to violet, with the shortest. Every color, every single shade, is just your brain's way of interpreting a slightly different wavelength of light. Kind of wild, right? So why this specific window? I mean, of all the frequencies, why these? It's no accident. Life on Earth evolved to use the most abundant light it could find. And it just so happens that our sun's energy output peaks, you guessed it, right in the middle of this visible spectrum. We see what we see because that's the light our sun decided to give us. Okay, now we're going to climb to the high-frequency, short-wavelength end of the spectrum. And up here, the photons are carrying enough energy to do a lot more than just warm things up or make a pretty picture. Up here, they have the power to fundamentally change matter. And that energy can be really dangerous. Most of the sun's highest energy ultraviolet radiation, the UVB and UVC rays, gets soaked up by the ozone layer in our upper atmosphere. This image of the ozone hole over Antarctica is a pretty stark reminder of just how critical that invisible shield is for protecting all of us down here on the surface. Now, the UV light that does manage to get through has two very different faces. Its energy is high enough to damage our DNA, which leads to things like sunburns and skin cancer. But that same germ-killing power makes it perfect for sterilization. And get this, our bodies have actually figured out how to harness it to produce essential vitamin D.
To create waves that are even more energetic, like X-rays, you have to really mess with atoms. One way is to just knock an electron out of its orbit. Then, when another electron falls down to fill that gap, it releases a high-energy X-ray. The other way is to just slam a super fast-moving electron into a target, forcing it to slam on the brakes and release all its energy as X-rays.
And it's that high energy that makes them so useful. X-rays have such short wavelengths that they can just zip right through soft tissues like muscles and organs, but they get stopped cold by denser materials like bone. This difference in absorption is what creates the shadow images that let doctors see right inside our bodies without ever making a cut. So from solving a simple kitchen mystery to understanding the stars, this one amazing concept, the electromagnetic spectrum, has given us an incredible toolkit for interacting with the universe. And there is no better symbol of this than this absolutely stunning photograph. This was taken during the Apollo 16 mission, and it's the first image of Earth ever taken in ultraviolet light. It shows us things that are completely invisible to our eyes, this huge halo of our hydrogen atmosphere and the glowing dance of the auroras at the poles. It's a picture of our world, seen through a different part of the invisible spectrum. The truth is, we live in an electromagnetic world. Your remote control uses infrared. Your Wi-Fi and cell phone use radio waves and microwaves. Airport scanners use X-rays. Nuclear medicine uses gamma rays. Literally, every part of this spectrum has been harnessed, weaving this incredible, invisible technological fabric that supports our entire modern lives. By understanding this invisible world, we've learned to see in totally new ways, to communicate instantly across the globe, and to heal the sick. And that leaves us with one final, really exciting question. We know what's here now, so what are we going to build, and what new wonders will we discover by seeing with it next?